Yes, sir. Gurman sir is there. Ma'am, you can start.
Okay, ma'am. Pooja ma'am, you can start.
Okay, ma'am. Ma'am, screen is visible.
Yes.
Yes, ma'am.
A very warm and pleasant afternoon to one and all present here. We welcome you all to our 11th session of 6 days online ATAL FDP, that is Quantum Machine Learning. I, Ms. Poonam Potraje, on behalf of Information Technology Department, AC Patil College of Engineering, Khargar, welcomes Dr. Gurmohan Singh sir and his teammate Dr. Tarun Kumar sir to the ATAL FDP on Next Gen Computing, Advances in HPC and Quantum Technologies for Data-Driven Insights. We are pleased to introduce Dr. Gurmohan Singh sir, Joint Director and Scientist E at CDAC Mohali, specializing in quantum computing and cybersecurity. With over 19 years of research experience, he has made a significant contribution to quantum algorithm, machine learning, and VLSI design. Dr. Singh holds a PhD from NIT Jalandhar and has supervised numerous PhD and master theses, publishing over 60 research papers. Its leadership has been instrumental in advancing quantum technology, earning him a prestigious award from CDAC in 2022. Dr. Singh continues to shape the future of quantum computing and cybersecurity in India. We welcome you, sir. Please accept our virtual token of respect.
Thank you, ma'am. Thank you for the gentle introduction.
Thank you, sir.
Should
Now-
I clear my slides?
Sorry, sir, you are not audible actually.
Yes, sir. Yes, sir.
Should I share my slides?
Yeah, sir, just a minute. Now, I request Dr. Gurmohan Singh, sir, and his teammate to start the session. Over to you, sir.
Okay, thank you, ma'am. My slides are visible?
Yes, sir.
Yes, sir.
Okay. So, good afternoon, everyone. So today my session is on quantum machine learning. So first of all, I will discuss a few theoretical things about quantum machine learning. And then thereafter, my colleague, Dr. Tarun, will showcase a use case of quantum machine learning algorithms implementation. So as we know that classical computing faces lot of challenges in solving hard problems, and for that actually new computing paradigm quantum computing is coming up, and it is predicted that within coming 5 to 10 years quantum computing will
Sir,
start.
can you please share your screen in full screen mode?
Yeah, now it is in full screen mode.
Yes. Yes, sir. Now it is visible.
Yes, sir.
Okay. So quantum computing is classical computing. We are challenges when a problem becomes multi-dimensional And in quantum computing, since we can handle multiple states simultaneously through principles of quantum mechanics like superposition and entanglement, okay, these are the two basic principles that provide us with the massive parallelism. In quantum computing, we are having superposition principle, which states that a qubit or quantum bit can exist in multiple states simultaneously. For example, if we are having 4 qubits, then the bit it can exist simultaneously in 2 raised to power 4 states, means 16 states it can simultaneously exist. Whereas in classical computing, we if we are having 4 bits, okay, then the maximum number possible combination of states it can exist is 2 raised to power 4 16. But at any instant of time, the classical computer can only be into one of those 16 states, not all 16 states simultaneously. In quantum computing, we can have qubits. Okay, if I am having 4 qubits, okay, then those four qubits can simultaneously represent 16 state at any instant of time. So this is the main thing in quantum computing that provides us with massive parallelism. So coming to quantum computing, how we can actually use quantum computing in machine learning applications. Okay, so there are a lot of applications in machine learning where we face problems related to computing. Okay, the class of those problems. This is actually we can say the area where quantum area where quantum computers they can pitch in. Okay, and they can help the classical computer to solve those kind of problems. So we can say that quantum machine learning exists at the intersection of both the fields quantum computing and machine learning. They basically leverage the quantum properties like superposition and entanglement to solve machine learning problems more efficiently. And they can provide us with the potential for breakthroughs in computation and data analysis, provided we have a sufficient number of fault tolerant quantum bits in the quantum computer. Okay, we can solve problems efficiently only in quantum computing, provided we are having fault tolerant qubits in that. So what are the actually advantages of quantum machine learning? The major advantage is speed up. Quantum algorithms, they provide us with exponential kind of speed ups, and they provide us with we can say advantage of handling multi high dimensional data representation, because qubits can exist in multiple states simultaneously, so they can handle much better way high dimensional data features. So they are very efficient in encoding the high dimensional data to quantum space. There are different kind of models, feature mapping models are there, which can encode your classical data to quantum space. So we can say that in machine learning seems to be infeasible in coming future. Once we have a sufficient number of qubits in a fault tolerant qubit, those problems can be solved very easily. So what are the actually applications of quantum machine learning? So quantum machine learning can have applications in multiple areas. So we can have applications in healthcare, we can have applications in finance, then AI and data science, energy and material sector, then finance kind of finance sector, also retail and marketing. So what are actually applications? The applications could be drug discovery, tumor classification, genomics, medical imaging. So when the COVID came, we all were expecting that why we are not able to make the COVID vaccine so early. Actually, in case of classical computing or even classical supercomputers, they take lot of time to compute all the combinations. For developing a successful drug, we need at least 10 years. 10 years are required to successfully test each and every combination of molecules that we want to use in the vaccine, so that their pros and cons of each and every molecule combination, they should be fully first, we can say, tested. In classical computers, if the molecules in your vaccine, they become more than 35, okay, so then it becomes very difficult for classical computer to simulate all the possible combinations of 2 raised to power 35 in very less time. But in quantum computers, 2019, Google claimed that they have achieved quantum supremacy. Actually, what is quantum supremacy? Quantum supremacy is when we say that quantum computers can handle any classical problems, or they can solve any classical problems in much better way or in much less time as compared to classical computers. That is quantum supremacy. At that time, Google claimed that they have solved a problem within 200 seconds using 53 quantum bit quantum processor, Sycamore. The name of the processor was Sycamore, which the classical supercomputers might have taken 10,000 years to solve the problem. So from here, you can well imagine how much quantum computers, they can help us in solving problems which are very difficult to solve using classical computers. So in finance sector, we can have portfolio optimization, then fraud detection kind of things, detecting some anomaly in multiple transactions. Crores of transactions are going in finance sector, banking sector. Okay, how to detect some kind of, we can say, anomalous behavior. Okay, observing all the transactions happening simultaneously. That is not actually possible using classical. However, if we are having some successful quantum computer or fault tolerant quantum computer with sufficient number of qubits, these kind of problems we can handle in much easier way or much easily. Then in cybersecurity, like we are having quantum key distribution, how we need to distribute key between sender and receiver. That is biggest issue, because anyone who, if you are sending some key over classical channels to some receiver, and in between someone withdraws, or we can say steals your information, okay, then whole of your whatever you are doing or transferring information, that become susceptible to misuse. So for these kind of things, quantum computing is much better. Then in AI and data science, training some kind of machine learning or AI model, in that way, the machine, this quantum machine learning can be very helpful. Then in materials, we can say material science, in energy and materials and developing some new combinations of molecules for some new materials, or developing some new materials. Okay, for those kind of things, we can use quantum machine learning. So in quantum machine learning, we are having multiple kind of, we can say, algorithms, like in hybrid quantum classical frameworks. The quantum layers integrated into classical machine learning models. Okay, the first we are having variational quantum algorithms. So what are actually variational quantum? There are two different types of variational quantum algorithm, two different classes. One is variational quantum eigensolver. They solve basically a problems by minimizing the expectation value of some Hamiltonian kind of thing. Then quantum approximate optimization algorithms, they are focused on solving combinatorial kind of optimizational problems, like traveling salesman kind of problem. Then we can have hybrid neural networks which use quantum layers within classical deep learning architectures. Then we are having quantum enhanced algorithms, means we are having some algorithm. What are quantum enhanced algorithms? Means algorithms are actually classical. However, we have speed up those algorithms using some quantum features in them, or implementing some, we can say, features in those algorithms which can be solved in quantum way much better. Those features we have implemented in quantum domain. So for that we are having different kind of algorithms like quantum k-means for clustering, then quantum support vector machines for classification, then quantum neural networks for employing parameterized quantum circuits to perform tasks similar to classical neural networks. These kind of things, they have all these kind of algorithms, they have been already developed. So if we compare classical versus quantum, then we can say we are having 5 different kind of categories. For example, supervised learning. In supervised learning, we are having algorithms like quantum support vector machine and quantum neural networks. So what are the key features? Basically, they are used for classification kind of problems as well as regression kind of problems. And what are the applications? The applications can be in image recognition, fraud detection, and there are a lot of other applications also. The unsupervised learning, we can have quantum principal component analysis kind of thing is there. We can reduce the dimensionality using similar to PCA. In classical PCA, we are having principal component analysis. Here we are having its counterpart, quantum principal component analysis. Then quantum clustering, we use quantum clustering for data regrouping. The applications could be in genomics, okay, genome sequencing, then market segmentation. Then we are having another field, reinforcement learning. In that, we can have applications in quantum regression, and then we can have key features are state optimization and policy learning. The applications could be in autonomous systems, autonomous vehicles, then game theory kind of things. So reinforcement learning is basically most of the times it is used in game theory kind of things. Then in hybrid algorithms, as already mentioned in previous slide, we have a variation on quantum eigensolver, then quantum proximate analysis kind of things. They can be used for quantum classical integration. The part which can be better solved in quantum, we can use these things there. Then the applications could be in optimization, energy modeling, then generative models. This is a new field in quantum. Actually, they have recently we have got these models for quantum generative AN kind of networks. So they can be, the features are data synthesis, distribution approximation. Then they could be used in anomaly detection as well as some feature extraction kind of things. So, what are the actually challenges in quantum machine learning at present? At present, the qubits or quantum bits or quantum computers that we use, they are noisy intermediate scale quantum devices. They contain lot of noise. Okay, when we put lot of qubits together, so it becomes very difficult or complex to control the state of those qubits due to the noise present in the system. So these are the problems, those need to be first solved at the hardware level. That lot of efforts are going into this direction to solve these problems. Then data encoding is also one of the bigger challenges, because in machine learning you have data sets. Okay, those data sets are in classical. Then how to map those data sets into quantum domain before applying some quantum machine learning or quantum algorithms on those data? You need to convert those data to, first of all, in quantum space. For that, although there are many feature mapping models have been built, okay, but still there is a lot of complexity in handling when some data set with some higher number of features come to us. Then how we can integrate it? Then it becomes computationally very expensive in quantum computers because quantum computers, you don't have actually fault tolerant kind of quantum computers, and access of quantum computer is not available at the present moment to everyone. It is within some high some few corporates only, like IBM, Google, then Intel, and then other INQ, the regulatory kind of things. They are having their own quantum computers, but they are not available to the general public for use. Although IBM is offering their quantum computers of some limited qubit, with some limited qubit access like 120 or 156 qubits for 10 minutes for per month. You can access their systems for 10 minutes only per month. So these kind of challenges are there in quantum machine learning at the present. So now from here over, I hand over to my colleague, Dr. Tarun. He will now proceed with this session. Over to you, Tarun.
Thank you. Good afternoon, everyone. So now we will discuss some tools and libraries. Like we have many platforms. IBM has provided us a platform that is Qiskit, and in Qiskit we can generate quantum circuits and machine learning models. And similar platform is Pennylen. This platform is generally for the hybrid quantum classical models. And the next one is the TensorFlow Quantum, and this why this TensorFlow is required, because it integrates the quantum computing with the machine learning platforms. So apart from Qiskit, Pennylen, and TensorFlow, there are many other platforms. One is by the Regity, and also by the Amazon, that is known as Amazon Bracket. By Google, there is CIRQ, CIRQ, and there are many more platforms provided by the big players. So what are the prerequisites to learn the quantum computing, or you can say the quantum machine learning? So the prerequisites would be the linear algebra, which includes the matrices and vectors, and then the quantum mechanics. Quantum mechanics basically, while we perform computation using quantum computers, we take advantage of this superposition and entanglement principles. So all those things that lie in the area of quantum mechanics. And then of course the classical machine learning, because the quantum machine learning is analogous to the classical machine learning with some enhancements. And then the resources, what are the resources to learn all those things? So you can directly go to the IBM Quantum Experience, the website provided by the IBM, and there you can also see their quantum computers, the real-time quantum computers that are on the cloud. And Xandu also provides the tutorials by the name of their website is by the name Pennylen. So, and these are two resources from where you can learn about the quantum machine learning. Of course, there are many other sources provided by the Amazon, Microsoft, and other companies. So what I'm going to do now is I'm going to present a demonstration to you on the Jupyter notebook for the binary classification of the brain tumors using the quantum support vector machines. So this is the methodology that we are going to follow. First, we will take the data set. The data set is in the CSV format, that is comma separated file. It's a comma separated file. You can also take any image data set, and for a beginner, you can take MNIST data sets for the classification purposes. And then we have we perform the data pre-processing on the data set. Then we visualize this data set, and then we split the data set into training and testing. And after that, we apply the PCA, that is the principal component analysis. Here we are using the classical principal component analysis, and then we perform the feature mapping. What happens is that the data we have is right now in the classical form, but we have to work on this data, and we have to perform computation computation on this data. So we have to by using these quantum algorithms, so we have to map this classical data to the quantum states so that we can apply the quantum algorithms on this data set. Then we will create an instance for the quantum kernel, and then we will feed this the output of the quantum kernel to the you can say to the quantum computers, or to the sampler. Sampler is also analogous to the quantum simulators provided by the IBM. Generally, we are going to work on the IBM platform right now. Then we will fit the quantum support vector machine based classification model, and then we will train and test, and then eventually we will get the prediction at the end in the form of accuracy, precision, sensitivity, specificity, and F1 score. And here at the left bottom, we have a diagram of support vector machine. What it does, it draws a hyperplane between the two classes to separate them, and this is how it classify between two classes. Also, you can use the multi-class classification methods by using quantum support vector machines. So what are the steps that we are going to use to create a quantum machine learning based model? So first we will take the data set. The data set is in the CSV format that I have already told you, and it is a brain tumor data set which contains 15 columns and 3,762 observations in total. It means we have 3,762 samples in this data sets. So we have two classes here. The one class is represented by 1, which is the tumor class, and the second class is represented by 0, that is the non-tumor class. Then we perform the quantum machine learning classification, which includes first the data pre-processing. Means the data is checked for the missing or null entries, and then we will draw the statistical summary of the brain tumor data sets to see if there are any extreme value outliers in the data set or not. And this data set contains a unwanted column, that is image column. So we have to remove this column from the data set first, and then we will split the data set into two sets, that is 70% training data and 30% of the test data. After that, we will employ the this principal component analysis. What we have, if you look at here, we have 15 columns, out of which one is class, and one column contains the name of the images. So the name of the images column is the unwanted one, which we have removed, and the one column is class column, and rest of the 13 columns, we have these 13 features. So the number of qubits we have to take is equal to the number of features, if you look at here. So what principal component analysis does, it reduces the dimensionality of the data set. Like if the number of features are 13, we have to use the number of qubits that is equal to the same number of features, that is 13. But if we reduce the dimensionality of the data set from 13 to 2, so for the two principal components, we have to use only 2 qubits, which means we are reducing the complexity of the quantum circuits of the classifier. If we are using the 13 qubits, then it will increase the complexity of the quantum circuits. So in order to reduce the complexity of the quantum circuit, PCA is used, which lowers the dimensionality of the data set. Is still intact while we reduce the dimensions by using PCA. And then we perform the quantum feature mapping. Quantum feature mapping, we will use the principal component analysis. After performing the principal, finding out the principal components which reduce the dimensionality of the brain tumor data set, the data values are still in the classical form. We have to convert this data into the let's say quantum states or quantum vectors. So it is required that we have to encode this quantum classical data into the quantum states. uh, for that we have to use some feature maps. So in Qiskit, or you can say in IBM Quantum Experience, you can find different many number of quantum feature maps. Out of them, we have mentioned, I have mentioned here, poly feature map, Z feature map, and double Z feature map. So in this case, we have used the Z feature map. So Z feature map is nothing but we have used Z gate. Z gate with some C naught gates. So the next thing is quantum. The next step is quantum kernel. The general task of machine learning is to find and study patterns in the data. For many data sets, the data points are better understood in a higher dimensional feature space. So for that case, we have to use the quantum kernel. The concept behind this quantum kernel is similar to the classical kernel, which maps the data points of the data set to a higher dimensional feature space. So if you look at here, we can mathematically perform it by taking out the inner product of the two quantum states, that is phi x and phi z, where x and z are the data points. So we can then create a quantum instance, or we can use any simulator, or we can use the sampler also. And along with that, we can also use the real-time quantum backends available on the IBM cloud. Then we implement the quantum support vector machine on the quantum support vector machine after defining the quantum instance, and we will take out the results in the form of accuracy, precision, sensitivity, specificity, and F1 score. So now I am moving forward to the Jupyter notebook. So I think we have some questions here in the chat box.
Yes, sir. There is one question.
Okay. Can we opt similar procedure for image data? How many qubit processing is allowed by IBM? You can also opt similar procedure for image data, but if the data is complex, like if you have any if you have MNIST data, then you can these models can perform well. But if you take any other, like you are taking the Brat's brain tumor data, then you have to employ other things first. Then at the end you can employ this quantum support vector machine algorithm. And this is not the only algorithm in the quantum space we have. We can also use the variational quantum classifier. We can also use Pegasus QSVM. And the kernels which which we can use can be the quantum PC. The PCA part which we can use can be the quantum part, can be the quantum PCA, or can be the classical PCA. You can use either of the PCA, and either of the algorithm that I mentioned, like quantum support vector machines, variational quantum classifiers. Also, there is Pegasus support vector machines, quantum support vector machines, and you can also apply some optimization techniques after that to improve the results. But for simpler data, you can use QSVM, and also there is this. Platform Penny. On that platform, you can also employ the quantum neural network. So if you are working on some complex images, then I suggest you can go to the Penny and use their platform for the quantum machine learning projects. Because I would like to add one more thing. This Penny is specifically designed for the quantum machine learning tasks. So that would be much better rather than IBM Qiskit. Okay, so now we are going to follow this Jupyter notebook. So this Jupyter notebook is only designed to classify the brain tumors in two categories, that is cancerous or non-cancerous. If you look at here, the brain tumors are the what are they? They are the abnormal growth of the cell that can be malignant, or you can say cancerous, and can be benign, that is non-cancerous. So it is entirely possible that you can remove the benign brain tumors surgically, because they have the homogeneous structure, and they are free of the cancer cells, and also they do not reoccur. But if we talk about the malignant tumors, these tumors have the heterogeneous structure which comprises of the cancerous cells, and they can only be removed by using chemotherapy, radiotherapy, or the combination of both. And these malignant tumors are potentially fatal. So if we look at the records presented by the International Agency for Research on Cancer, So they have published that in India, over 28,000 cases of brain tumors occur every year, and we see a lot of that. That is, 24,000 people die because of the brain tumor in India. So the early diagnosis of these brain tumors is very important to save as many lives as possible. So this is the methodology. Again, almost the same methodology that I have mentioned in these slides. So we will take the data set in the CSV format. We will pre-process the data. We will visualize the data and perform the exploratory data analysis. Then we will split the data set into two categories, that is training and testing. After that, we will employ the principal component analysis, then followed by the feature mapping, and then we employ this quantum kernel, which takes the data set into the higher dimensional quantum space, and then we apply the quantum support vector classifier, and then we fit the model and then perform training and testing. And in the end, we get the results in the form of accuracy, precision, sensitivity, specificity, and F1 score. So for that, we need some important libraries. Like these are the libraries that we are going to require to run this notebook. So first one is import NumPy as NP. NumPy is required for the mathematical operations, and then we are going to use Seaborn as SNS. Seaborn is for the for plotting the graphs, and then we will also import the pandas as PD. So pandas library is used to load your data set, and then we are going to use this matplotlib.pyplot as PLT. This is also for the plotting purposes. And then there are some sklearn libraries. We are going to use these libraries like standard scaler, min-max scaler. These are for the scaling of the data set. And then we are going to use this PCA, principal component analysis. This PCA also belongs to the sklearn library. And then from that from the same library, we are going to use accuracy score, classification report, and confusion metrics. And to split the data set into training and testing, we are also going to import this train test split. And ROC curve also belongs to this sklearn library. So this is used to plot the AUC ROC curve. And then we are going to use some Qiskit libraries. Like we have this Z feature. We have to import this Z feature map and double Z feature map from this Qiskit.circuit library. So in this notebook we will use either of these two feature maps. And then we will also need to import quantum kernel, that is fidelity quantum kernel, from the quantum machine learning library. So there is this, we are not going to use the Pegasus QSVC because we are going to implement only the quantum support vector machine, that is this QSVC. We have to import it from the quantum machine learning, Qiskit machine learning library. And also for the sampling purpose, we will be requiring this Qiskit.primitives library. And then for the fidelity, we have to import the compute fidelity, and that also belongs to the Qiskit machine learning libraries. Import warning. This is nothing but to ignore if any warning comes up, like warning regarding to deprecation of any library. So if I run it, if you have laptops handy, then you can also run run this notebook with me. Or later I can share the notebook with you with the environment.
Sir, we would love to run, but we don't have the data and the code.
So I will provide the data and the code, but you will also be requiring the environment where all these libraries are installed, right? So maybe via email or something, I can share it with you, and later on you can run this notebook by your own. So the data we are going to use is the CSV data that is available on the Kaggle. So we are going to import the dataset by using this PD library, that is pandas library, and the dataset is stored here in the dataset and codes folder. If I go there, it's this dataset. So we have some. This is the dataset we have. We have this image column which is redundant, so we have not used it in the notebook. And then this column is the class column, where the 0 means the no tumor class and 1 means the cancer class, and 0 means the no cancer class. And we have some statistical features like mean, variance, standard deviation, etc. And we have some second order features also, like contrast, energy, ASM. So these are the features, and the length of the dataset is up to this 3000. 3763. So this is not a very complicated data set. This is a very simple data set which does not include any null values, any outliers, huge outliers. So I have used this data set to give you idea that how you can implement the quantum versions of support vector machines on the y is our class that is at the index 1. So it is at index 1, this is class, and x is the features that are from index 2 to 15. So they are from mean to is there can you also see this Google Meet dialog box? Ma'am, can you hear me?
Yes, yes.
Yes, sir. Yes, sir.
Is this blocking the notebook?
Partially, yes.
So I don't know how to minimize it, because there is no option of minimizing it. Maybe I can resize it.
It's fine
Okay.
now.
Okay. So when I print the head of this data set, it will give us the 5 rows of the data sets. So these are the this is the data set. So first I have to run this cell and then this. If I print the x means the features that we have this 5.520. This is the mean, and then y, if I print y is the class, and the components of the class are 0 and 1. The shape of the dataset is initial 200 samples, right? I have not taken the complete dataset for the demonstration because it might take more than 2 or 3 hours to run the whole notebook. Not to run the whole notebook, to fit the model. If I am taking the large number of samples, so that is why I have taken very less amount of samples here. That is 200. I can take the complete data set, but it will take 2 to 3 hours to fit the model. So it is advisable that the first take less samples to check if the model is fitting or not. So if I group it, we have 110 samples from class 0 and 190 samples from class 1. So this is the information of the dataset by using this function dataset.info. All those things that I'm doing right now they are the classical ones. I think most of you have already used all of these things. Like we have these are the number of features we have, and then there is no null count, no null values, right? So, or we can also check if there is any null value or if there is any missing value in the data set or not by using the ISNA method. If I use this method, so it gives you the result in Boolean form, that is true or false. False means that no value. And by using the sum method along with this ISNA method, we can count the number of missing values in each column of the data set. So if we check here, we have no null values. Like in image, there is 0 missing values or 0 null values in class. So this data set does not contain any missing value or any null value. So we will visualize the data set then. So what I have done is I have visualized the dataset by using the pair plot method from the Seaborn library. So what it does, it gives us the correlation between the features. Like it gives us the graph between homogeneity and mean, energy and variance. Between all the features, it gives us the correlation. So if I look at the graph, so we can see that the class, if you can look at here, the class 0 is the green one and class 1 is the orange one. So these classes, they are like we can use the QSVM to draw a hyperplane between them. So we can easily classify these two classes, right? If you look at all these graphs, that here the hyperplane would be like this, here it would be like this, right? So by visualizing it, we can say that this so there are some more correlation between the features, that mean versus variance, right? So blue one belongs to the class 1 and orange one belongs to the class 0. So by drawing out the correlation between all those features, we can also conclude that we can use the quantum support vector machine to classify the both of the classes, right? So the next step is to split the dataset into training and testing. So X-train means the training features, and X-test mean the test features. Y train means the training class or label, you can say, or Y test means the testing labels. So we are going to split this data set uh, into in the ratio of 80 to 20. Like 80% of the data set we are going to feed for the training, and 20% of the data set we are going to use for the testing purpose. So now we will perform some scaling. Like if you look at the data set, there are the values are like this. This is 5.52. Then we have this 417. Then we have this 20. Then it is in 0.005. So we have to scale this down to a particular scale. So the scale we are using here is 0 to 1, right? So all this data set data points comes between the 0 to 1. Now we will this is how we use the min max scaler to scale down the data set to in between 0 and 1, and we will fit it. Then what it does, it transform your X train and X test by applying it on the X train and X test respectively. So now we are going to use the principal component analysis, that is the PCA. So from if I till this cell that is the cell 13, we have 13 features, right? We have 13 features and one class. So after employing the PCA, what PCA does, it reduces these 13 features to the two principal components, right? From higher dimensional space to a lower dimensional space. So how we can do it? We can use the PCA by using this method PCA.transform on the X train. So the X train will be transformed, and then similarly we will apply this to the X test also. So if we plot the graph, so you can look at here that we have only two components, that is PCA component 1 and PCA component 2, right? So you can also by looking at the graph, you can also say that we can draw a hyperplane between those two classes, or those support vectors of belongs to the two classes. So now we are going to do the quantum part. So like I said, if we have 13 features, we have to use the 13 qubits. But what it does, it will increase the complexity. To reduce the complexity, we have used the PCA, which lower down the data set from 13 features to the two principal components. So that is why we are only using the two number of qubits here. And then we are doing the feature mapping. For feature mapping, we are going to use the Z feature map. If you go to the website of IBM, you can see there some feature maps like Z feature map, double Z feature map, poly feature maps. So out of them, I have chosen only this Z feature map. And then we are going to use the sampler. The sampler function, what it does, it samples the output from the quantum feature map, right? And then these circuits will be fit to the fidelity of the this quantum support vector machine model, right? And then we are going to use this quantum kernel, which takes the quantum features to the higher quantum higher dimensional quantum space, right? And in the argument, we have to employ the fidelity and the feature map. So I'm going to run it. Now we are going to use the quantum support vector classifier. So this is how you use it. This is how we use it, just like the classical QSVM. Uh, in classical QSVM, you give in the argument the kernels like the RBF, sigmoid, etc. Here we have defined the quantum kernel. So we are giving this quantum kernel in the argument of the this quantum support vector classifier. Then we will fit the model by using this classifier into X train and by using the X train and Y train. And then we will get the testing score of this model. So if I run it, maybe it will take 1 or 2 minutes. We have to wait for it. The accuracy was 92.5%, I think. We have to wait for 1 or 2 minutes so that the results appear. Meanwhile, if you have any questions, then you can ask me.
Participants, please unmute yourself and ask the questions. Any question from participant side? Please unmute yourself and ask.
If we are supposed to do it for any other image network, then
Sorry?
I mean, there were two questions from my side. One was if I'm supposed to do multi-class classification,
Okay.
and then more than 4 or 5 features, then how do I take it? I think for the free version, we can only take 5 qubits at IBM's Qiskit.
For how many features you have? 5 qubits. 5
IBM
features.
yeah, free वाला version के लिए IBM Qiskit में, so I can take only on the real machine run करना है, तो I can take only 5 qubits.
No, why 5?
So उससे ज़्यादा free how will I get a free network?
No,
Free
the 5 qubit quantum machine you are talking about is now not in the on the cloud. So if I show you here, IBM, there are only 3 quantum computers available on the cloud now. And they are way more than the 5 qubits. Like they are maybe 127 qubit, I think.
So how to get access to this 27 qubit wala by IBM account only? Then the waiting will be too long, sir.
It's not 27, it's 127. First, you have to create the account on this IBM Quantum platform, right? Then you will see API token here, right?
Yeah, I got this. And then if I'm trying to execute, the waiting time is too long, sir, for this.
The waiting time is too low. That is because there are a lot of jobs that are in queue.
Okay.
Right? If I will show you. If I go there and see, these are the IBM Cave, Brisbane, and Sherbrooke. Right? These are the free ones. Right? So you can use up to 127 qubits, qubit model on these 3 quantum computers. So if I open it, you can see currently there are 117 jobs that are running on this computer. That is the pending job. They are in queue.
Yes.
When this 117 jobs gets completed, thereafter your job has to be there and it will run, right? So this is the waiting time.
Okay.
Before before your job, there has to they have this computer has to clear these 117 jobs, right?
Then how to track my job on it, sir?
You can track it by here. Here you can
In my login.
here like in 10th of April 2024, I have sent this job on this online simulator, IBM Quantum simulator, right? So when right now the status is completed, right? But when your job is in the queue, it will stay in queue.
Okay.
When it is in progress, then it will say in progress. Like when it is running, then it will say it is running, right? When it is completed, then like this, it will say completed,
Okay.
right?
Yeah.
And yes, you can perform the multi-class classification, multi-class classification problems, or you can build these kind of models by using quantum support vector classifier. Okay. Okay, so the program we have run the program. So it is saying that this test score is 95%. So this will we can also generate the classification report. If there is any other question.
Any other questions, participants? Please unmute yourself and ask.
Sir,
Yes, ma'am.
sir, if anyone is willing to implement this QSPM
Mhm.
using MATLAB code,
No, not MATLAB. It is not available on the MATLAB.
only Python.
Only Python.
Okay, that's my question. Thank you.
Okay. We need the code. Okay, I will share the code with you. Okay. So we have got the classification report. So it is saying that for class 0, we have the precision of 93, and for class 1, we have the precision of 100%. Hello, can you hear me?
Yes, sir. Yes, sir. Yes.
Hello, can you hear me, ma'am?
Yes, sir.
Yes, sir. Yes.
Okay. So when my laptop has turned off, or this was the last cell that I have run, right? So although the notebook has run completely, so we have achieved the 95% of the accuracy in that uh, by running this notebook on the by using the brain tumor dataset for the QML based uh, classification model, right? So if there is any questions regarding this, then you can ask me now. If any other questions are there. The notebook was complete.
Participants, please unmute yourself and ask the questions.
Sorry.
Sir, I guess there is no more questions.
Okay. So that is all from my side, ma'am.
Okay. Just a minute, sir.
Okay.
Ma'am, screen is visible.
Yes, ma'am.
Yes, ma'am.
We would like to thank Mr. Dr. Gurmohan Singh sir and his teammate Dr. Tarun Kumar sir for enlightening the session on quantum machine learning. Their expertise has not only shed light on the theoretical underpinnings but also provided the practical insights into the potential applications of this transformative technology. Sir, please accept our virtual token of appreciation. Thank you, Tarun sir.
Thank you, ma'am.
We would also like to acknowledge and express our thanks to all the attendees. Thank you all.
Okay, ma'am. Thank you.
Thank you. Thank you, sir. Participants, please be there in the meet for the next session. We will continue the meet with the same meeting